This video lecture is going to be on Section 3 through Section 5 of Chapter 11 on intermolecular forces. So today in your book here, I'll provide those as reference pages for you today. You're finishing up with hydrogen bonding last time. And thinking about hydrogen bonding, these were special dipole-dipole attractions. And again, it's hydrogen with nitrogen, oxygen, or fluorine. So you have a covalent bond that's an intramolecular force. A hydrogen bond is an intermolecular force. Remember, that goes in between molecules. This is a special type of intermolecular force. What happens is there's a huge electronegativity difference between nitrogen, oxygen, or fluorine compared to the hydrogen. So this really electronegative element, whenever we get hydrogen bonded to it, exposes this hydrogen nucleus, which is really, really attractive to other molecules around it. You got this figure in your book here with the water and the snowflake, and see how that looks. That's really strong because that hydrogen is wanting to give away that electron so readily. So what we can see are these ion dipole interactions. If you notice here with the chlorine, the partial positive ends of the water molecules attach. What ends up happening with those partial positives, they line up with the partial negatives. And those partial negatives of the chlorine line up with the partial positives of the water, which is the hydrogen there. Over here we have the sodium over here that has a positive end because it's an ion attracted to the negative end of the water molecule. This is why NaCl dissolves in water so easily, because it's attached to those partial positive and negative parts of the water molecule. The strength of this force really pulls it in ionic substances in the polar solvents. This chart is really big. This is how you can tell what type of intermolecular force is available. Kind of walk you through the chart here. At the top, if you have ions that are present, something that's ionic, and again, that's a metal and a nonmetal, usually bonded together with a positive and a negative charge, you've got ions. So if you have ions present, you need to ask if the molecules are polar. Remember, polarity depends on the shape, and it depends on the electronegativity. Let me get that off the screen here for us. So whenever you're looking at it and you're trying to figure out what type of intermolecular force it is, the ions are a real key to that. So if you got ion dipole, you're dissolved in something ionic. You can have ionic bonding if there's no polar substances and everything is ions. Now, where you don't have ions present, you have to figure out if a molecule is polar or not. Remember, unshared electron domains usually will go to some sort of polar molecule. So if there are hydrogens present and it's an N, O, and an F, this section right here, then that leads directly to the hydrogen bonding. If it is polar molecules and there's not hydrogen with N, O, and F, then it's dipole-dipole. If there aren't any polar molecules left, we have the London dispersion forces. Remember that London dispersion and dipole-dipoles are examples of van der Waals forces, the weakest of the intermoleculars. So as we think about those forces, it's ion dipole, hydrogen bonding, then dipole-dipole, then those London dispersion forces are definitely the weakest out of the group. So we talked about shape earlier, about how that can work with this. These intermolecular forces can affect if they go and they dissolve. They can affect the boiling points. You look at acetic acid over here on the side. It's got a hydrogen bonds with neighbors. If you take a look at how its boiling point's affected, that boiling point is pretty high, 391 Kelvin. Again, that formula has hydrogen bonding sites. Now, at propanol here at the bottom, notice that boiling point drops to 370. It does have some polar parts, but a majority of the molecule is nonpolar, and there's dispersion forces holding the others. So the more sites we have for hydrogen bonding, the higher that boiling point would be, and the tougher those molecules would be to break apart. Viscosity is a property of solutions. This is its resistance to flow. One thing that is usually misunderstood with viscosity If you've got viscosity that's high, that means the liquid doesn't want to flow very much. This figure over here on the side talks about motor oils. SAE 40 is a heavier weight motor oil. High viscosity doesn't pour out very well. That's usually used in high temperature engines, so the engine heat won't break it down as easily and change its state or make it thinner to use. If the engine is smaller, you get SAE 10. That's used for a lower viscosity, easier to pour, not as much temperature is cranked up. Notice how this goes with intermolecular forces. With hexane, smaller molecule, to the -4, as we build molecules down to decane, it goes up to 1.42 times 10 to the -3rd. So again, if you have a bigger molecule, you've got more intermolecular forces, so you've got a higher viscosity. The other thing is intermolecular force decreases with temperature. Remember, temperature is the average kinetic energy of the system. More kinetic energy breaks apart those attractions. It's going to make them flow easier and lower the viscosity. Surface tension, you can see the bug floating on the water. The water molecules make a thin film on the surface because they're attracted to each other with hydrogen bonding. This intermolecular forces, if you think about it, you've got these water molecules that are bent because of the unshared pairs. And if you see those molecules bent with each other, and you get a hydrogen molecule linking with the other oxygen, you got a partial negative, you've got a partial positive. And when those link together, it kind of makes almost a saran wrap type of thing. Saran wrap's too much because that's a solid, but it's a thin sheet, really, is a way to think about it over the top. This really only occurs with strong bonds that happen. It kind of pulls them and makes a tight skin on the top. That's why the bug's able to float on water, why water molecules really want to stick together. That's surface tension. There's an inward force where the molecules are pulling in against each other that create this thin film on the top. And again, surface tension increases with intermolecular forces. Phase changes. We think about the states of matter, solid, liquid, and gas. These are all vocab words that I think you're pretty familiar with. Maybe some of the ones you're not. Sublimation is solid directly to a gas. That's endothermic. Remember back to the thermochemistry, endo means energy is being added into the system to move those molecules apart. Melting and fusion are the same things. Those are also endothermics. Vaporization, liquid to gas, that's endothermic. If something condenses, it's got to lose that energy out from the system to the surroundings. So the surroundings may gain energy, but the substance itself would lose energy. Therefore, those molecules can slow down. Therefore, their attractions can get closer to each other. Those are the exothermics where energy is released. This is why whenever you sweat and you have vaporization that happens, you yourself, the system, you feel cooler, but that energy goes out to the surroundings and is lost out to it. So they absorb the energy, they leave, your body feels cooler because it imparts energy into the water molecules. This is a great graph. This talks about heats of fusion. That is the energy needed to change something from a solid to a liquid. If you look at these, there's also heats of vaporization. That's going into being a liquid to a gas. Sublimation is that direct change. If you take a look at all three of these, you can make some determinations about intermolecular forces. Notice that mercury is at the top of the list over on the right. Mercury has the highest heat of sublimation. It's got the highest heat of vaporization and the highest heat of fusion. Again, we would have metallic bonding, which is an intramolecular force between all those molecules, which is really strong. Water would have hydrogen bonding, which is an intermolecular force in that list. Diethyl ether does not have hydrogen bonding with it because you don't have N, O, or F with it. So this would experience some dipole-dipole attractions. So it's second, and then butane is completely nonpolar. So it has the lowest of all those attractions. So we can use intermolecular forces to explain why things melt, freeze, boil, and phase change at a variety of temperatures. And you can see that in this graph by looking at how all those look. Heat of vaporization, that's again changing from a liquid to a gas. Again, it follows suit of intermolecular forces. Heat of sublimation is directly solid to a gas. This is a heating curve. And what happens is, take special note of this heating curve in your text, because the flat lines are the most critical. While the average kinetic energy of the system is not increasing overall because the temperature flatlines, what happens is all those molecules are overcoming their intermolecular forces to change states. So down here, we don't get complete melting until all the water solid is melted to liquid. So we're trying to overcome intermolecular forces on the flat lines. Up here at the top, everything's trying to change phase. We're trying to break all those forces. That's why when you're cooking food on your stove, it tells you to get it to a rolling boil, because that's a consistent temperature that will stay until all of the water boils. We're trying to overcome all those intermolecular forces. So while we're still adding heat to the system, the heat doesn't go to increasing the average kinetic energy, it's going to breaking down the intermolecular forces. Vapor pressure, this is how we can get molecules to break free and go from the liquid to the vapor phase. As we increase temperature, more molecules have the ability to break free. If you take a look at this graph, when you have higher temperature, you have more area underneath of the red. That means you've got more molecules that can break free. Lower temperatures, there are fewer molecules that have the threshold to go. Notice not every molecule has enough kinetic energy to break into the vapor phase. Only a fraction of them do. Because remember, temperature is the average kinetic energy of the system. Not every molecule has got enough kinetic energy to break free. That's why when you watch water boil in a pot, some of the molecules will start to bubble and boil off, while the rest of the water is still a liquid. We're trying to get all those molecules to get enough kinetic energy to break free into the gas phase. So as more molecules escape, the pressure they exert increases. Well, that makes sense, because pressure is dependent upon the number of moles of molecules in the gas phase. If we don't have anything that's going to vapor phase, the pressure is zero. We start adding this, starts changing, now we start getting more gas, and then there's an equilibrium, which is the balance between liquid and gas. Notice we've increased the vapor pressure. So the more molecules that escape the liquid, the more vapor pressure we get. And that makes sense with the gas laws. Vapor pressure is when we reach equilibrium, dynamic. It's a steady rate of change. What that means is the same number of molecules leaving the liquid phase into the gas phase equals the number of molecules going into the vapor phase. So the number going into vapor equals the number into liquid. What happens is when that rate, those are competing things. Going to vapor is one way, we'll just say that's the vapor direction, and going to liquid is this direction. This is something where you see the double arrows for equilibrium. Those two rates become equivalent. That's when vapor pressure, we have equilibrium vapor pressures. This is a great diagram. Looks at the vapor pressures of when things are boiling. When you get enough molecules to start boiling, their vapor pressure is overcoming atmospheric pressure. So if you look here at diethyl ether, when it gets to 34.6 Celsius, it's going to boil. We can get enough molecules to get enough kinetic energy to break free, and their vapor pressure equals atmospheric pressure, and it goes. Look at, and diethyl ether's got mostly dispersion. Ethyl alcohol's got some dipole, pulls to 78.3. Check out the hydrogen bonding here with water up to 100. If you've noticed, water is going to boil at 760 torr, 1 atmosphere, at 100 degrees Celsius, if that's true. If your air pressure changes by elevation, that changes your boiling point. The higher your elevation is, the lower your air pressure is. So water will actually boil in mountain regions at lower temperatures. So the boiling direction, say in the Rocky Mountains, are going to be different than what they are here in Illinois. What happens is you can see in the water bucket or in the water pan, you'll see bubbles form at the bottom first, but it won't boil. But when you get enough pressure built up in the water, where you increase that vapor pressure, the bubbles come to the top and you see the rolling boil. When you see that boil, it's hit that vapor pressure, it's hit that equilibrium. And it will stay at 100 until all those water molecules have changed. Ethylene glycol is antifreeze. It's a big molecule. It's got hydrogen bonding sites, it's got dipole sites, and it's a large mass molecule. That's why it's used for antifreeze. Now this is the natural log of vapor pressure is inverse to the temperature. Now what does that mean? If you were to graph this and look at pressure and temperature, if we have a higher temperature, we can look at a greater pressure. We'll talk more about this graph in detail in class. So this relationship is the Clausius-Clapeyron equation, and this relates the gases and energy all together. I'll explain more of this in class with some of our examples, and we'll stop there. So this video lecture goes up to phase diagrams, but not past those phase diagrams. So check that out, and we'll talk more about this in class.